Hello, I'm Michael O'Connell, and in today's video we're going to apply Bernoulli's equation to a problem in which we have a sealed tank of water that's leaking out at the bottom. So let's draw that here. So we have some sort of cylindrical tank, let's say. I'm going to draw a small little hole that maybe we've punctured at the bottom so that we have some water in here, and then we have some flow outward. Okay, so what we should first consider is our dimensions of our cylindrical tank. So we have a height of large H, cross-sectional area A sub C. Then we have the cross-sectional area here. We'll call that A sub whole. Okay? Now, why can we apply Bernoulli's equation to this type of problem? Well, what we want to do is model how our fluid height, we'll call this H, okay, and that's going to be the fluid level of the water inside our cylindrical tank. We want to model how this changes with time. So if we have a very, very small hole that we've punctured, due to the surface tension of water, there is not going to be air that's coming back in. So we know that, yeah, some water is going to flow out, and then we're going to reach steady state, okay? So that would look something like this, right? So our fluid level decreases and then it reaches some sort of steady state here. Okay? Bernoulli's equation is a steady state equation. So how does this work if we have our fluid level dropping? The key thing here is we're able to do this because this velocity, and I'm going to label these, so this is going to be position 1 and position 2 is going to be at the hole. And I think that is visible on your screen there, which is good. What we are going to say is that the velocity of our fluid surface, right, at the level moving down is extremely small. Now, why is that? Well, hopefully you remember here, if we were to do the continuity equation on this, right, we would get this, right? So the volumetric flow rate of fluid moving through here in our cylindrical tank is equivalent to the volumetric flow rate through there, which is at our punctured hole. I should put V sub 2 there, okay? So what am I trying to say here? Well, if our cross-sectional area of this cylindrical tank is very, very large with respect to the cross-sectional area of a little hole that we've poked, then this V sub 1 is going to be very, 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 very small. Okay, so that's why we're going to take it to be 0 when we apply Bernoulli's equation to this. What else might we have to consider? Well, notice the way I've drawn this is that we actually have a headspace up here. There's not much room, but this isn't water up here, right? This is air. Another thing we're not going to consider in this problem is the vapor pressure of the water at some given temperature. We're also not going to consider the temperature changes with time in this problem as either. And then we're also not going to consider frictional heating. So before we move forward, I think it'd be helpful if I actually write out Bernoulli's equation in the form that we're going to use. So we have a pressure change from position 1 to position 2 over the density of our fluid, okay? Then we have a change in kinetic energy. And then we also have the change in the gravitational potential energy. And we can use Z for that this time. Okay. This expression, because we're ignoring our fancy F term, this is the frictional heating, okay? Because we're ignoring that, and that would be the difference between the internal energy and the heat added to a system. We're ignoring this, so this is 0. Okay. And then we also said that the velocity of our fluid surface moving down is 0, so we get rid of that as well. Okay, so what do we have to describe? I actually want to start with this term on the right here, because it's the easiest, right? Well, it at least looks like the easiest. But we have to be really careful, and that's why I wanted to start with this. So we have some height. We're talking about our fluid level. That's what we're trying to model. So we want to use this H. Okay, so where do we pick our 0? This is where we have to be careful. So if I choose my 0 at position 1 up here at the fluid surface, and then I choose my height to be h down here, that's not going to work, right? Because this fluid level is changing. So what are you going to do when you have 0 changing, and then your variable, which really is supposed to be your variable fluid level, is not changing, right? That's kind of a head scratcher, exactly, because it doesn't work. So what you want to do is the opposite, right? We have h here. If we take g as positive 9.8 meters per second squared, that was really bad handwriting, then we can rewrite that part of our expression, right? So that's going to be position 2 was 0. So that term here is going to be minus gh, right? 0 minus h. Okay, and then we already have the v2 squared over 2. You might be wondering, okay, so how are we going to do this, right? Because we want to end up making a plot of how the fluid level changes with respect to time. The way we're going to do that is by taking advantage of the continuity equation, as I said, which gives you the volumetric flow rate. Specifically, because we are interested in finding the velocity of fluid that's exiting out of this punctured hole, okay? Because we know what the cross-sectional area of our hole is, okay? So that's why that's going to be useful for us. And using the volumetric flow rate expression, which I'll denote as Q later in the video, that is where we'll be able to get a differential equation that basically describes how the height or the fluid level is changing with respect to time. Then we're actually going to use Colaboratory, Python specifically, there to solve that differential equation and get a nice graph. Okay, so what about our pressures then? What is this going to look like? Now, this is a very, very interesting and very important concept here. So we're going to have some initial pressure in here in our headspace, okay? And that's the pressure of our air. To make this problem a little easier for this video, we're going to say that we have our atmospheric pressure outside our cylinder here, our tank. And we're going to say initially that the pressure of the air inside here is equivalent to the pressure of the atmosphere, okay? So P sub I would be P sub ATM, okay? Now, is that going to stay the same? No, of course not, right? So the fluid level is going to drop, which means the volume is going to increase. We're neglecting changes in temperature. So we would definitely say that the pressure is certainly going to decrease, okay? Now, another thing that would actually stay constant, and this is what's so important for us when we apply the ideal gas law here for the air in our headspace, is that the moles of air in our headspace doesn't change, okay? It doesn't change with time because there's no leakage up here. There's only leakage down here, okay, at the bottom. That's key to understand. So we just have the fluid that's exiting. So we can write an expression using the ideal gas law, right? So we would have P sub I. I'll use, because we've said that's the same as the atmospheric pressure outside, I would like to do that. V sub I over RT. Okay, what's V sub I? We should probably re-express that. That's not too difficult, right? We have some height and then the cross-sectional area, so we would multiply those. That height is going to be the difference between the height of our whole tank, actually, and the initial fluid level. So that's another important variable to note, right? So, yeah, we would have the cross-sectional area here, and then the height of our cylindrical tank minus h sub I, where h sub I is the initial fluid level, right? We have to define everything in this expression as initial because some of these things are about to change. But that's why this expression for the moles of air is so useful, is because the moles of air does not change, okay? And that's what we're about to see. So, again, I've defined this at our fluid surface up here that's going to be dropping. We're at position 1. So let's use this expression for the moles of air that doesn't change to help us write an expression for the pressure at position 1, okay? So what exactly is that going to look like? Well, that's going to be nRT over V, right? So V sub 1. Now, V sub 1, this time, again, unlike V sub I, which was constant because it was just our initial volume of air up there, V sub 1 is going to be changing because our fluid levels drop. Specifically, it's going to be increasing, right? So, once again, we would have our cross-sectional area, and large H, it would definitely depend on the height of our tank. But now we want to subtract this H. This H is variable. It's changing. That's our fluid level, okay? Because this is going to be decreasing, right? So you can see in our expression there how the volume of air here in our headspace is going to be increasing. Then we have N, number of moles of air, times the ideal gas constant R, and then the temperature. So this, N, this is constant, right? So that can plug right into there. And so hopefully you're able to follow what I'm about to do on the screen, because hopefully you can see here with these terms, there's a lot that can be canceled out, which is fantastic. Okay, so we have the cross-sectional area of our tank in the denominator and in the numerator coming into the numerator, so this is gone. Okay, and then you have the same situation just in reverse with the product of the ideal gas constant and temperature, so those are gone. Okay, so what are we left with? Well, we're left with the pressure of the atmosphere and then the height differences there at the start. So we get this expression for the pressure at position 1. Oh, sorry, that's actually what we just canceled. I'm looking at the wrong thing. So it's that, and then we have H minus H sub I over large H minus H. Okay, so that's your expression there. Okay, that's extremely helpful. So if you're following along with our Bernoulli's equation, this is a check. We've got that, right? In fact, this is what we're solving for because it's going to be useful in using the volumetric flow rate equation to get our differential equation that describes how the fluid height is changing with respect to time. Then we already know this stuff. We took care of that. We made sure that we put our 0 at the bottom of the tank, which was critical because otherwise the point that we set to be 0, if that was at our fluid surface, that'd be a problem because it's changing. So we need the pressure at position 2, right? So we need the pressure right here at our hole, okay? And this is an extremely important concept. So normally when we have some sort of expansion, position 1 and position 2, smaller area, this is just the continuity equation that I just wrote down, right? Earlier in the video. Fluids coming in here, well, smaller area, again, so this is going to be at a higher kinetic energy for your fluid. Okay, so what's happening here? Well, obviously the kinetic energy is decreasing, so how does that balance out in terms of energy? Well, this is what's called pressure recovery, right? And we see that in the Bernoulli's equation, right? Ignore any height change for that expression. Also ignore frictional heating just as we're doing here, okay? So, well, that has to show up somewhere. It would show up here. You would get pressure recovery. What's interesting is when we do a sudden expansion, that's not what happens. So a sudden expansion would be like, okay, we're going through a normal pipe, right? And then boom, like you're out. And that's exactly what we have, right? I mean, this would look very, very similar to what we have with our tank, right? You have fluid. Well, I mean, the visual will be a little bit different. But yeah, you have fluid that exits and there's a sudden expansion, right? Because, I mean, this is completely vertical. Okay, out into the atmosphere. So what does that mean? If there's no pressure recovery, that would imply that pressure at position 2 is actually the same as the pressure of our atmosphere, right? Because there was no increase in pressure because of the sudden expansion. Okay, so this actually means that P sub 2 is equal to P sub ATM, or the pressure of the atmosphere outside, which is great. Okay, so now from there, we can actually rewrite our Bernoulli equation here. Let's get a little more light in here. There we go. Just wanted that back on. Okay, so if P sub 2 is P atmosphere, then that can be factored out, right? So we're looking at this expression here, and we have to make sure we don't forget the density of our fluid, okay? But this part should be pretty easy. So if we factor out P sub atmosphere, and then we would just be, oh, and we can also factor out the density, right? Because that's multiplied, or that's in the denominator for this difference in pressures, okay? So that works. So this would be a 1, and then here we just have this fraction for P sub 1. So H minus HI, H minus H. Okay, what do we have next? So here is where we would want to start moving things around. We want to solve for this term. So we're trying to find the exit velocity of the water that's leaving our hole. So that's why I'm actually going to put this term on the other side of the equation. So we have to remember that this is all set, this part is all set equal to 0. So I'm just going to switch those fractions there to move this to the other side, where we would get this, okay? And this is good as well, because remember, we have the minus GH. So that can come to the other side as well, okay? So what is this equal to? Well, what would that leave us, basically? Yeah, and don't get confused with these. These are kind of like separate things. They don't have to do with that 0. We would have the V sub 2 squared over 2 on this side. So we can actually multiply all of this by 2. And then, if you can still follow me here, square root. That's going to be V sub 2. I know that's kind of crazy, so I'm going to just rewrite it. So what do we do next here? We're in the home stretch. We want to describe the volumetric flow rate of our fluid that's leaving, right? So we know that this is going to be V sub 2 times A sub whole, right? From the continuity equation, as I said before. We can also express the other side of that continuity equation with the negative of the differential change in volume with respect to time. Why is it negative? Well, we are losing volume, right? Fluid is exiting from the bottom of our tank. So what would this be? Well, that's going to have to do with the dimensions of our tank, right, in terms of volume. So we would have negative A sub C, which is the cross-sectional area of our cylindrical tank. And then here is our beloved differential that we've been searching for this entire video, right? That's the DH, right? That's the fluid level that we're after, okay? So the differential change in the fluid level over, of course, dt. So that is what we're after. So we can rearrange this into the way in which we're going to want it in the next part of this video, actually, where we're going to want the differential change of our dependent variable over the differential change in our independent variable on the left-hand side set equal to the right-hand side expression, which is going to be what? Let's see. Looks like negative V sub 2A sub whole. And then we would just, dividing both sides by A sub C, right? Okay. So obviously this expression for V sub 2 you would plug into there. But this, overall, this is the differential equation that we're going to be solving with SciPy dot integrate solve IVP, which is a very good method for solving systems of ordinary differential equations. And for us, we don't have a system, we just have one. So that will be extremely cool. That's the next part of this video, and we're going to be plotting the change in the fluid height over time. Now let's solve this problem in Python. So we already derived the differential equation that we need. So what I've done here is I've imported numerical Python, so that will allow us to use certain functions that we need to do mathematical operations when we code this, and our solve IVP, so that's the method that we're going to be using to solve our differential equation, and lastly plotly, which has the make subplots import there, and that is what we're going to be using to make a plot of the fluid level with respect to time.
Okay, so I want to talk about the solve IVP method very briefly here. I was looking it up beforehand, and we need to supply a function for the right-hand side of our differential equation. And fortunately, I solve the problems that I do for these videos before I make the video, obviously. And I do that in Microsoft Word, so that's also where I have all those constants, like the height of our cylindrical tank, and the initial fluid level, the density of the water, the atmospheric pressure, you know, you name it. Obviously, the cross-sectional area of our hole and the cross-sectional area of the tank as well, acceleration due to gravity, all that good stuff. I think I actually named them all there. Okay, so that's over there. And I solved this problem, and here I solved it just the way we did on the whiteboard, right? Where we have the left-hand side has the differential change of our dependent variable over the differential change in our independent variable, so that's dH over dt, okay? And then this expression here, right, so we have A sub h times V sub 2, and V sub 2 is the exit velocity of the water from the bottom of our tank. This expression on the right-hand side, that's going to be, actually, if I may have said it wrong before, that's going to be the return of our function. And actually, you'll see here with the solve IVP method when we're doing this to solve differential equations, so that needs to be a return. What I mean to say is that needs to be an array, okay? So, and you see that if you scroll all the way down here and you go to returns, you see y, so that's our dependent variable, needs to be returned as an array, okay? And what else do we have in here to talk about? Okay, also, the initial value is also an array, as you see there. Why not? Okay, so let's define a function, right? We'll call it RHS for right-hand side. We have the time first, the dependent variable, or the independent variable, then the dependent variable y. So we only have one differential equation that we're solving. Sometimes, and actually oftentimes, you'll be solving systems of differential equations. So that's why it takes this independent variable, the initial value, as an array, okay? Because you'd have multiple differential equations, so you'd have many different initial values. But in our case, we're only solving one, so we have our changing height that we'll set equal to the first value, okay? So we'll index the vector array here of y with 0, okay, for our first value. Now, it will help us a lot because we have that crazy radical equation for v2. We can use numpy, the square root. We want to do this in our function, okay? So here I'm going to type in this expression there, okay? This is our velocity, right? And that's the velocity of the fluid that's exiting. So that's what I'm going to type into here. Now we're ready to continue. So we have our return. That's going to be negative a. That, okay. And notice I have that in the brackets, so that's an array. Okay. So what would we like to do next? Well, we're going to be plotting this, so we need a certain time span, right? And that needs to be supplied here, as it says, with floats as a tuple, okay? So let's specify an ending time. How about 10 seconds? Seems reasonable, okay? Let that load. I like to hit Shift Enter each time. That's a mistake I made about 1,000,000 times in my old material and energy balance videos, and I'll probably continue to make in these videos as well, but that's okay. I can try to remember as much as I can there. So what we want to do first maybe is let's test this out, right? So we have our right hand side, so we can supply some sort of time, 0.2 seconds, and then our initial height, right? And we want to put that in there as the list, and that should work for us. So this is the rate of change in our fluid level at this point in time, okay? And that is basically how this works. Now, we want to use the solve IVP method to actually find the solution of our differential equation, so that's what we should do next. So first we put in our function, which we called RHS for the right-hand side. Then we need our time span. So here we can start at 0 and then go to our end time, Tn. And then those are in parentheses. Start and end separated by a comma so that it's a tuple. Okay? Then we have that vector of our just the initial height this time. Okay? What are we going to have next? Well, we do want to use some sort of method for solving this, so we're going to use the Radu method. A little slow, but it's pretty robust in its calculations, so it's fairly accurate. And the last thing we need is dense output. Dense output is actually going to give us, as we specify this to be true, we get our solution attribute out of here. Ooh, okay. We've run into a problem. So this is something that we will have to address. So perhaps we ran this too long, right? So it says that the array in here, which it's probably talking about this array, right, can't contain infinites, and then NaN is not a number, okay? So we probably got something imaginary, perhaps a negative number in our square root here. That will be a problem for us that we will have to address. For now, let's just decrease our time span. Okay. Let's see what we get. Awesome. Okay, so you see here that we have some times here, and then we have a solution attribute sol. Okay. So if we assign this a value z, we can actually grab the solution attribute, which is really cool. Okay. What's even more cool is you can put in time. It's a 0.4. Let's see how high our fluid level is. Okay. It's less than 0.9 meters high, so it's probably correct, right? It went down. Okay. So that's really awesome. So that's basically going to be the basis, that's the framework by which we're going to be able to make a graph, okay, of how the fluid level changes with respect to time. Let's use Plotly to actually make a plot of our solution here, right? So here we can have some sort of time span, right? Okay, and we can linearly space these arbitrary time values that we create, right? So we're going to start at time 0, and then we'll go to our end time that we specify. And then how many points do we want linearly spaced? Let's do 500. Okay, so plenty of points there that we're going to have on our scatter plot. Okay, what do we want next? Well, we have to define something, so let's say fig. And this is where we are going to use the make subplots function there. Okay, and then now we can add a scatter plot. And here's where you're going to have your x and your y. So our x is going to be the independent variable, so that's our t plot. Now y, we have z.sol, right, because we want the solution attribute. And then as I showed before when we put in 0.4 seconds and got the fluid level, that's what we're going to do here, except we have all of our times, right, that we're going to plug into here. The last thing we can do is we can update the dimensions. Okay, so update and then underscore, we have layout, and we can make this look nice, right? So we have width and height. Let's make them the same, nice little box. Okay, and then just so that it's easier on your eyes, we can do Plotly dark. Oh, I'm gonna need that. Let's see if this works. And I did something wrong here. I spelled update wrong. So I need to update my update. Uh-oh. That's not good. We just don't have anything, okay? So I clearly forgot something here, and there is an attribute that I need. Specifically, we have to remember that this is returned as an array, right? So I'm going to need to index that, okay? And there you go. Is this what we want? It's part of it, right? But it's not exactly what we want, right? We're interested in seeing at what time, when we puncture a hole in the bottom of our tank, at what time do we reach steady state? Because it's a very, very small hole, so some water is going to leak out. But as I said, in the past there, with the surface tension, you're not going to have air that flows back in. So it's actually going to stop, and you're going to reach, a new lower fluid level. And that's our steady state, right? So all derivatives with respect to time go to zero. So we should see a flat line, right? And we don't see that. So to try to see that, we can increase our time span a little bit. So we can go to 3 seconds. Now remember, I believe it was 10 or 20 seconds before. Okay, that's a little better, right? So we start sloping a little bit. When we did 10 seconds, we ran into issues. Let's try 5 seconds and see what we get there. Okay. There's something that you might have caught there. So here, it does give us the graph. So we see that we do reach a steady state somewhere in here. Okay, around between 4 and 5, which is awesome. However, we do have this issue. So we have an invalid value encountered in the square root. Now, why is that? Well, this is the same problem we had if I increase this to 10 seconds again. Now, I think we're ready to address this issue. Okay? So, yeah, then you get something like that. That's not what we want at all. Okay, so what happened here? Well, basically, we have an infinite or not a number somewhere, and as I said, we probably have a negative value here in our square root. Okay, now we can try using numpy to get rid of this. We can do absolute value. Okay, that's one way to address this type of problem. Ooh boy, well that's not going to work either, is it? Because this isn't wrong. Or sorry, this is wrong. Right? So this was where we reached our steady state, and then somehow the fluid level kept dropping again. So you punctured a hole, water started flowing out, it stopped for like a brief second, and then it just kept flowing out. So that just doesn't make any sense. That's not right. Now, why is that not right? Well, this absolute value, again, let's go back to our equation here, okay? And this is where understanding what's actually physically happening is of very, very high importance. So this H here, this is the fluid level of the water in our tank. And that is what's changing. Specifically, it's decreasing, right? Because we set our 0 at the bottom and we set H at the initial, at the fluid surface, okay? So it's decreasing. So as that decreases, this value here in the denominator increases. Remember that this is a fraction where the numerator is the difference between the height of our actual tank and the initial fluid level. Okay, so this is always pretty much instantly, this numerator is smaller than our denominator, such that this value in here is negative, right? And thus this product is negative. That is added against this product of G times H. Obviously this 2 here is factored out, so we can ignore that. Okay, so at some point down the line, as we're decreasing our fluid level over time, this in here, this becomes negative, and we get that negative square root, okay? And that's where you get this issue, okay? So what do we need to do here? Well, absolute value just is not going to cut it, because that's just a sheer misrepresentation of what's happening, okay? What we're going to need to do is specify the time at which this inner part here is equal to 0. Now, why is this important? When that's 0, what is V sub 2? That's our exit velocity of water that's flowing out of the tank. So that's 0. So that's actually when we reach our steady state, okay? Which at that point, there is no more accurate calculations that the Radu method that's solving our differential equation can perform. And in fact, it's actually just going to keep having round-off errors, right? Because it's increasing a small increment of time and recalculating the fluid level, right? So then it goes a little bit too far, right? And you get a negative value. Okay, it goes to absolute value. So, it's really just 0 minus 0 that it's really at, right? Something like that inside here, where really your exit velocity of water has actually reached 0, but it just keeps recalculating values. So if you take the absolute value of that, well, your graph just continues, which is not what we want to see at all, okay, because that's not what happens. It should just stop like that. So what we need to do, if we specify this event, at which the exit velocity of fluid leaving our tank is 0. We need to actually terminate our integration here. We need to stop solving everything, okay? And that's what I wanted to call your attention to here with the solve IVP method for these differential equations, and specifically solving them in Python like we're doing in this video. So what I'm about to talk about here are events, and these are really cool. I had never heard of these before, and you'll notice that this is new. This is not something that we did in material and energy balances. So what is happening here? Well, basically each event occurs at the zeros of a continuous function. So we have a continuous function, and yes, at some point that exit velocity is 0. So that's what we're after here. You see this terminal here, this attribute. So that's what you can put on after you create a function for your event, okay? And that's going to be that continuous function that you're looking to find. Okay, at what time does this become 0? This attribute allows you to actually terminate integration if the event occurs. And that's exactly what we want to do. So let's do that. Let's define a function. So we're going to call this v2 events, or we'll call it event. And as you saw on there, it's going to take in t and y again, of course, and we're going to supply the initial value, right? Again, we're just using the index of 0 there, right? Because we only have one differential equation that we're dealing with here. Okay, what is going to be our return? Well, this is actually more simple than you might expect. It's already in here, right? So this is when this continuous function here is equal to 0, that's when the exit velocity of the water is equal to 0, okay? So that's perfect. The next thing we want to do then is have our v2 event dot terminal. Ooh, terminal. That's a tough one to spell for me. True. Okay? Great. So that is in there. Now, this is something that we have to specify. I'm going to get rid of this so that we can look at this, at all the information that it gives us. So this is that events, if you can see on the screen. I love when it does this because it's so helpful. So none is the default, so we have to actually specify what's going on here. We'll put this in as a vector there, okay? And that's consistent just like we did with our initial value for the dependent variable. And what would we put in? Well, we're just going to put in this, whoops, so that we copy that name there, v2 event, this function, okay? And let's see what we get out of that. A termination event has occurred. Now we're at 10 seconds, so that should, alarm bells should be going off, telling you that yes, we have reached steady state, okay? And let's see what we have here. So this is our solution attribute that I've talked about before. It did perform this successfully, which is great. It gives us some time values in an array, and then this is the time events. Notice that we have an array within an array. This 4.59 seconds, roughly 4.6 seconds, that is when the integration terminated, which means that's when we reach steady state. That's when the volume of air, if you will, in our headspace stopped increasing, or you could also say that's the point at which the water stopped exiting from our cylindrical tank. Okay, so what do we do next? Well, now we have to actually plot this. So let's see where we will go from there. So what we notice here is that t events is an attribute now within what our solve IVP has returned to us. So that's something that we can use just like we use z.sol and then specified our t_plot for all of our time data points that we want to use to make our plot. So let's do this real quick. So let's enter that. And then basically all we should have to do here to wrap up our video is z.t_events, right? So we need that attribute. Now, if I didn't make it clear before, to make this visible, if we look at what z is, this attribute is an array value here when we reach steady state within an array. So we're going to need to do some double indexing here. So that's going to be 0 to get this array out of this initial array that's returned, and then another index 0 as well. Okay, so this time we should get a nice plot, and we do. Okay, this looks great. And notice that this terminates at that point at which we reach steady state. Now, I will admit to you before I wrap up this video, for the sake of time, I'm not going to worry about this too much, but there is a very, very, very slight difference between this value, this 4.59, and the theoretical value that should be obtained for the solution here, which I believe is 4.56. I'm not quite sure why there is that discrepancy, but because it's quite small, I don't think it's really worth addressing. And the concepts that I covered in this video are all the same. And we address the same conflict of, oh my gosh, like we're getting infinites, not a number inside our square root. And again, that's just part of when you have square roots, or even if you're just doing division. If a denominator goes to 0, that can be a problem anytime you're doing any type of math with Python code. So that's just something to be aware of. So I think this whole idea of using events was extremely helpful, and I hope you learned a lot from this video. So if you need to take a picture of this, this is what your actual final plot. This shows how the fluid level of the water in our tank decreases over time until it reaches a steady state, okay? And that's, of course, with no air seeping in that small hole that we punctured. So thank you so much for watching this video. I hope you learned a lot, and I'll see you next time.